Hello and welcome to Sleepy Story Facts, a quiet little corner of the night where everything is allowed to slow down. Out there, the world can feel bright and busy, full of messages, movement, and noise that asks for your attention. In here, nothing needs to be solved. Nothing needs to be rushed. This is a gentle bedtime story, a nighttime story made for adults who want to fall asleep softly and stay asleep as the mind drifts into deep sleep at its own unhurried pace. Tonight, instead of traveling across wide landscapes you can see with your eyes, we'll wander into a realm you can only sense with curiosity. A place where a single particle of light can behave like a spreading wave and also arrive like a tiny, precise point. A place where the emptiest vacuum is not truly empty, and where invisible fields quietly hum beneath everything you touch. As the story unfolds, you'll hear about quantum fields and soft, strange rules, about particles that can be linked across distance, and about experiments where the simple act of checking seems to reshape what's happening. Some ideas may feel a little mysterious at first. That's okay. You don't need to understand every detail to relax. You can let the words pass by like slow-moving clouds, keeping only what feels comforting and letting the rest fade into the background like a half-remembered dream. And if these calm, curious moments become part of your gentle bedtime, if this relaxing story helps you unwind at the end of your day, you're always welcome to support the channel in whatever way feels natural. But for now, there's nothing you need to do at all. Just settle in. Let your shoulders drop. Let your jaw loosen. And if it feels safe, allow your eyes to close as the night holds you in quiet. Now we'll begin. In everyday life, physics seems steady and reliable. Things fall when you let go of them. Time moves forward in its familiar rhythm. Light appears to travel in straight lines, and the world feels solid beneath your feet. It's a comforting set of rules, the kind that lets the mind predict what comes next. But if you could shrink down, smaller and smaller, past dust and skin and cells, down to the scale of atoms, those sturdy rules begin to soften around the edges. At the quantum scale, nature stops promising certainty. Instead of clear paths, there are likelihoods. Instead of neat, single outcomes, there are possibilities. A particle may not behave like a tiny marble rolling along a track. It behaves more like a delicate blur of potential, as though it's spread across space in a gentle haze, waiting. And cause and effect, the way we're used to it, can feel less straightforward. In this hidden world, it can seem as if events don't always line up in the tidy sequence we expect. Sometimes more than one outcome appears to be available at once, until a moment arrives when only one becomes real in a definite way. Quantum physics can feel like discovering a second set of rules tucked quietly underneath the first. The everyday world doesn't exactly disappear. It's still there. It's just not the entire story. Beneath what feels solid and certain, there's a softer foundation, subtle, strange, and deeply important, quietly shaping everything we know. Most people will never directly see this world. The pieces that make it up are far smaller than what visible light can resolve. They remain beyond ordinary sight, like a secret written in ink too fine for the human eye. And yet, even unseen, the quantum realm matters. It's woven into every breath you take. It's part of what makes matter stable, what makes chemistry possible, what makes the familiar world behave the way it does. In this realm, particles can behave like ripples. They can appear briefly and fade. They can even seem to occupy more than one place, in a sense, until something pins them down. The mathematics used to describe it can look almost like a language from another planet, so abstract that even experienced physicists sometimes admit they can use the equations expertly while still feeling a quiet humility about what the equations truly mean. This isn't just reality in miniature, it's reality in a different mood. One of the first gentle doorways into this strange world is the idea that energy is not always smooth and continuous. For a long time, it was natural to imagine energy like flowing water pouring in any amount, divisible into smaller and smaller portions without end. But when scientists looked closely at how heat and light behave, they found something surprising. Under certain conditions, energy arrives in small, discrete packets, not a continuous stream, but tiny steps. These packets are called quanta, and you can think of a quantum as the smallest unit of energy a system can take in or give away, like the smallest coin in the universe's quiet currency. This simple, strange idea helped explain why hot objects glow with particular colors, why atoms absorb and emit light in distinct patterns, and why nature sometimes prefers jumps over smooth transitions. And it became one of the early foundations of modern quantum theory, the beginning of a new way of understanding the world. Then comes another idea, one that sounds like a riddle spoken softly in the dark. In the quantum world, matter can move like a wave and yet arrive like a particle. A wave spreads. It overlaps with itself. It creates patterns. A particle seems local, specific, like a tiny dot, and yet when light passes through two narrow openings, it forms an interference pattern, the kind expected from waves. But when that same light is detected one piece at a time, each photon appears as a single, distinct event, arriving in one spot, not smeared across space. Even electrons behave this way. So do atoms. Under the right conditions, even larger molecules can show hints of this wave-like nature. It suggests that quantum particles are not always tiny objects traveling like little billiard balls. Instead, they behave like probability, spread gently through space, describing what might happen, until a measurement brings one clear outcome into focus. And that leads to one of the most soothing and strange thoughts in the whole field. In quantum mechanics, observation is not completely separate from what is observed. Measuring a system changes it, because measurement requires interaction. In experiments like the double slit, the behavior can shift depending on whether information is gathered about which path a particle takes. Without that information, the system produces wave-like interference. With it, the results become more particle-like, as though the possibilities narrow into a single, definite story. It can feel, at first, as if reality responds to being noticed. But you don't need to solve that mystery tonight. You only need to let it be a soft idea, something to listen to as you rest, while the mind loosens its grip on certainty and becomes comfortable with quiet, gentle the more you linger with these ideas, the more they open into quiet, weightless questions. If the act of measuring can change what happens, then what is the world like before it's measured? Is reality already decided, simply hidden from view? Or does it remain gently undefined, like a scene still forming in soft fog, until interaction asks it to settle into a single shape? Some people approach this as a physical question, grounded in experiments and equations. Others feel it as a philosophical mystery, the kind you can hold in your mind without needing to solve. Either way, the thought that observation and outcome are intertwined has fascinated scientists for generations, and it still carries that same hushed sense of wonder. And here, the story grows even stranger in a way that is oddly soothing once the mind stops demanding certainty, because quantum physics doesn't just suggest that measuring can change a system. It also tells us that nature places gentle limits on what can be known. At the same time, in the everyday world, it feels reasonable to believe that if measurements become precise enough, knowledge becomes complete. If you know exactly where something is and exactly how fast it's moving, then you should be able to predict what it will do next. Classical physics encouraged that comfortable confidence. But at tiny scales, that confidence softens. The uncertainty principle, often associated with Werner Heisenberg, describes a fundamental trade-off. The more precisely you pin down a particle's position, the less precisely you can know its momentum. And if you lock momentum down tightly, position becomes more blurred. And this isn't simply a problem with human tools, like a blurry camera lens or a ruler with markings too wide. It's more like a quiet rule written into the structure of the universe itself. Certain pairs of properties are not simultaneously exact. The uncertainty is not a mistake. It is part of the design. So, at the quantum level, the future cannot be predicted with perfect certainty. The best that can be done is to describe chances, to map out probabilities, to speak in the language of more likely and less likely rather than guaranteed. For a mind that's tired, that can actually feel like permission. You don't have to control everything. You don't have to know everything. You can simply let things be and allow yourself to rest. From here, the next idea drifts in one of the most dreamlike concepts in all of physics: superposition. In quantum mechanics, a system can exist in a combination of possible states at once, not switching rapidly between them, like a hummingbird's wings blurring into a shape, but genuinely described as holding multiple possibilities together in a delicate balance. An electron, for example, can be described as having more than one spin state in its mathematical description. A photon can be described as taking more than one path. The system is represented by a wave function, an elegant, shifting expression that doesn't give a single answer, but instead contains a whole spread of potential outcomes. And then, when an interaction occurs, when something acts like a measurement, the system no longer behaves as a blend of possibilities. One outcome becomes the one that's experienced, and the other options no longer appear in that same way. In the ordinary world, superposition feels impossible to witness directly. Everyday objects are constantly interacting with their surroundings: light, air, heat, vibration. So their delicate quantum possibilities don't remain isolated for long. The softness collapses into something firm. But in the quiet laboratory conditions where quantum systems can be gently shielded, superposition shows itself again and again as a repeatable, testable part of nature. And it's not only a beautiful concept, it's also useful. Quantum computers, for instance, are designed to take advantage of these overlapping possibilities, using quantum bits that can represent combinations of states, allowing certain kinds of calculations to be explored in parallel rather than one at a time. Even if quantum computing feels far away tonight, the deeper message can be simple. At the smallest scales, reality is not built out of certainty. It is built out of likelihood. In the quantum realm, a particle's location, momentum, or other properties aren't fixed like labels already attached. Instead, they are described by a spread of probabilities, like a gentle map of what could happen if you were to look. The wave function evolves smoothly, almost like a quiet tide shifting under the surface. And then, when interaction happens, when a system meets the world in a decisive way, one outcome appears, selected from the range of what was possible. This randomness unsettled many brilliant minds. Einstein, famously uncomfortable with a universe that seemed to rely on chance, resisted the idea that probability was truly fundamental. But time, experiments, and careful testing have continued to point in the same direction. Probability at the quantum level is not just a placeholder for ignorance. It seems woven into what reality is, and yet there remains a lingering mystery, soft, persistent, and still unsolved in a final way. What exactly is happening in that moment when many possibilities become one experience? Some interpretations say something like a real collapse occurs. Others suggest there is no collapse at all, that all outcomes happen, and experience simply follows one branch of a larger structure. Some views treat the wave function as a tool for predicting what will be observed, rather than a literal description of what exists. No single interpretation has one universal agreement, and perhaps, in a way, that uncertainty fits the theme. The quantum world does not always offer a single story with a single ending. It offers several, gently overlapping, and to help people feel the strangeness of it, one of the most famous thought experiments arrives, quietly, like a story whispered in a dim room. Schrödinger's cat. Imagine a closed box, sealed from view. Inside is a cat, and a device connected to a quantum event, something like the decay of an atom that has a certain chance of triggering poison. Until the system is checked, quantum theory describes the decay as not settled into one definite outcome. So, in the strange language of superposition, the setup is described as holding both possibilities at once. And if you extend that description up to the cat, it leads to the unsettling image of the cat being both alive and dead, until the box is opened and the outcome becomes definite. This was never meant as a recommendation for how to treat cats. It was a spotlight aimed at the boundary between the tiny quantum world and the large everyday world, showing how odd the rules become when applied to familiar things. And still, the cat remains a powerful symbol. A simple scene that lets the mind picture the paradox, and then slowly let it drift away again, like a thought dissolving as sleep deepens. The night continues, quiet and steady, and as you rest, the ideas can become even softer, almost like a slow lullaby made of science. Because in the quantum world, two particles can become connected in a way that doesn't match everyday intuition. This is called entanglement. Entanglement is what happens when two quantum objects are prepared so closely together, so carefully linked, that they can no longer be described as fully separate things. Instead of each particle carrying its own independent story, they begin to share one combined description, like a single sentence written across two distant pages. And then, when one is measured, the other seems to respond immediately. Not because a message has raced across space like a whisper, traveling faster than light, but because the pair was never truly two independent systems in the first place. Their properties belong to the whole. It can help to imagine it in a gentle way, like two perfectly matched gloves placed in two different drawers. When you open one drawer and see a left glove, you instantly know the other drawer holds the right glove. Nothing has traveled between them. You simply revealed something about the shared set. Now, quantum entanglement is deeper than gloves and stranger than drawers. But that calm idea can keep the mind from tensing up. Entanglement is less about messages flying through space and more about the universe, allowing some things to be described as one connected pattern, even when the parts are far apart. Physicists have created entanglement in laboratories using photons, electrons, and small collections of atoms. The connection can be delicate, too. It's easily disturbed by interference from the environment, heat, stray interactions, unwanted measurements, like a soft thread that can fray if it's handled roughly. But when the conditions are carefully protected, the link holds, and it hints at a layer of reality where separate is not always as simple as it feels. Now picture this slowly. Imagine two entangled particles drifting apart, one traveling in one direction, the other in another, until they are separated by a great distance. Across a city, across a continent, even across the curve of the earth. And then a measurement is made on one of them. In that moment, the outcome found here is correlated with the outcome that would be found there, in a way that feels immediate, as though the universe is answering both questions at once. Again, it's not that a signal has crossed the space between them faster than light. Quantum physics doesn't require that. Instead, it suggests something subtler. The particles did not carry independent, preset answers for the measurement. The pair carried a shared description, and measurement reveals a matching relationship between them. That's one reason entanglement can feel so dreamlike. It asks the mind to relax its ordinary sense of distance and to consider that separateness might sometimes be more like a convenience rather than a fundamental truth. Even Albert Einstein found this deeply uncomfortable. Einstein preferred a universe that behaved with clear rules and definite properties. And when he considered entanglement, he disliked how it seemed to challenge that picture. He famously described it as spooky action at a distance, not as praise, but as a complaint, a way of saying it felt too strange to be the final explanation. Together with collaborators, Einstein helped present a challenge. Perhaps quantum mechanics was incomplete. Perhaps there were hidden details, unseen factors, that would restore the comforting idea that particles have definite properties all along, whether observed or not. But as the decades passed, physicists designed careful experiments to test these competing ideas. They created pairs of entangled particles, often photons, and measured them in different ways, comparing the observed correlations to what classical hidden variable explanations could allow. Again and again, the results supported the quantum prediction. The correlations were stronger and more specific than any simple hidden variable picture could account for. Over time, these tests became more precise. Loopholes were closed, distances grew larger, conditions became cleaner, and the same conclusion kept returning, steady as a heartbeat in the dark. Entanglement is not just a clever trick of mathematics. It is something nature genuinely permits, and as strange as it sounds, it appears to be woven into reality itself, an invisible connection with no cord, no thread, no ordinary pathway, and yet a connection all the same. For a bedtime story, there is something unexpectedly comforting in that. A reminder that even when things feel far apart, even when the mind feels separated from calm, from rest, from ease, the universe still holds forms of connection that cannot be seen, yet still exist. So as you breathe slowly, and the room stays quiet around you, you can let the thought of entanglement drift through your mind like a soft idea. Not a problem to solve, just a gentle image of the cosmos being more connected than it appears. As the night goes on and your breathing grows slower, it can be comforting to notice how these ideas don't rush you. They simply unfold, one gentle step at a time. Entanglement can feel so strange that it almost invites the mind to search for a hidden explanation, something tucked behind the scenes, something ordinary that would make it all feel less mysterious. That was one of the hopes many scientists held, including Einstein. The thought was simple. Maybe the particles carry secret instructions, hidden variables that decide the outcomes in advance. If that were true, then entanglement would only look magical because we didn't know what information the particles were carrying. But then came a quiet, powerful idea. In the 1960s, physicist John Bell found a way to turn that hope into something testable. He developed a mathematical check, now known as Bell's theorem, that can distinguish between hidden local instructions and the stronger connections predicted by quantum mechanics. Bell showed that if a theory relies on local hidden information, meaning no influence travels faster than light, and properties are set ahead of time, then there are strict limits to how strongly two distant measurements can be correlated. Quantum mechanics, however, predicts correlations that can go beyond those limits. And when experiments were performed over and over with increasing care, the results consistently favored the quantum predictions. In other words, the simple, tidy picture of particles carrying private, per-written answers was not enough to explain what nature is doing. So the universe seems to ask us to loosen our grip on at least one familiar comfort. Either the world is not fully local in the way everyday intuition suggests, or objects don't always possess definite properties in advance, at least not in the straightforward classical sense. Either way, Bell's work gently closes a door on the purely classical explanation and opens a wider, quieter view of reality, one where connection runs deeper than distance. And there's an interesting twist here, too. Something once considered a philosophical oddity became the groundwork for practical tools. The very correlations that once sounded like a paradox are now at the heart of quantum information science. Ideas like quantum cryptography and secure communication that rely on entanglement's unusual structure. Now, with that in mind, another concept drifts in, softly named and often misunderstood: quantum teleportation. Despite the name, this isn't about moving a person across space in a flash of light. Nothing large is transported. No object vanishes from one place and appears in another. Instead, quantum teleportation transfers a state, the exact quantum identity of a system, from one particle to another, using entanglement as a kind of bridge. In a gentle outline, it works like this. First, two particles are entangled, creating a shared quantum relationship. One particle stays with the sender, and the other is carried to the receiver. Then a special combined measurement is performed involving the sender's particle and the particle whose state is being teleported. After that process, the original state is no longer present in the first place, and the distant particle takes on that exact state. No physical matter has flown across the gap, but the quantum information, the pattern that defines the state, has been recreated at the destination. It's been demonstrated in real experiments with different types of quantum systems, and it's considered an important ingredient for future quantum networks, ways of linking devices with ultra-secure quantum communication. And if you let yourself hear it as part of a bedtime story, it almost sounds like a lullaby about identity. Not the movement of objects, but the gentle handing off of a pattern. From here, the story becomes even more spacious. Some physicists and theorists have explored a bold possibility: that space-time itself, the very sense of distance, geometry, and here versus there, might emerge from vast webs of entanglement. In this view, space might not be the stage on which physics happens. Space might be something built, moment by moment, out of deeper quantum relationships, like a fabric woven from invisible links. This idea is still speculative and not settled science, but it has inspired serious work because it hints at a bridge between quantum mechanics and gravity, two frameworks that both describe nature beautifully, yet don't fully fit together in a single unified picture. And whether or not spacetime truly comes from entanglement, one thing remains quietly striking. If entanglement is as natural as quantum theory suggests, then the universe is not just a collection of isolated points. It is a web of relationships, a kind of ongoing, silent conversation between systems, connections forming, fading, and forming again as particles interact. Even though entanglement can be fragile, disrupted by noise, heat, and interference, there are also conditions where it can persist in surprisingly robust ways. in certain special states of matter, large groups of particles can behave collectively, holding onto shared quantum relationships far longer than expected. And this matters not only for understanding nature, but for building new technology, because if entanglement can be protected, guided, and used on purpose, it becomes a resource, a tool for computing, communication, and sensing, quietly powerful, and still only partly explored. For now, though, you don't need the technology. You only need the feeling of it. A calm idea floating through the dark, that the universe may be stitched together more deeply than it looks, and that even emptiness might be full of hidden connection. In the quiet of this bedtime story, the mind can drift closer to the smallest things, not to solve them, but simply to feel their gentle strangeness. Let's begin with the electron. It's one of the most familiar characters in the unseen world. Electrons flow through wires, helping lamps glow and screens shine. They help atoms hold together, shaping chemistry, biology, and everything that feels solid in your hands. And yet, when scientists try to treat an electron like a tiny ball with a clear edge, it refuses. In many experiments, the electron behaves as if it has no internal structure at all, no little parts, no measurable diameter in the ordinary sense, and still, it doesn't behave like a fixed pinpoint sitting in one exact place. Instead, an electron is described as spread out, like a calm, invisible cloud. Not a cloud made of mist, but a cloud made of probability, a gentle map of where the electron is likely to be found if you decide to look. Around an atomic nucleus, this map forms shapes, patterns that follow quantum rules, like quiet geometry drawn in darkness. In one moment, the electron may be more likely to be close to the nucleus. In another, the probability shifts, and it's more likely farther away. The cloud isn't the electron smearing like paint. It's the universe offering a range of possible answers, until an interaction makes one of them definite. And in that strange balance, point-like, yet spread out, there's a perfect lesson of the quantum world. Things are not always either-or. Sometimes they are both, depending on how they are asked to appear. Now, let's turn toward light. Photons, the tiny packets of light, have no rest mass. They're weightless in the way we usually imagine weight. And still, they carry energy. They also carry momentum, which means that when light strikes something, it can give a small push, a soft pressure. It's subtle, almost unimaginably gentle, but it's real in the open quiet of space, where there's no air to slow things down. That tiny push can add up over time. Sunlight can nudge dust. It can slightly alter the paths of small objects, and engineers have even imagined, then built the idea of solar sails, wide, reflective sheets that catch the momentum of sunlight and slowly glide forward without fuel, guided by nothing but the steady touch of photons. And on very small scales, light can be used like careful fingers. Focused beams can hold and move microscopic particles in a technique often called optical tweezers, useful in delicate research, where tiny objects need to be guided without being crushed or touched, so even something weightless can move matter. Even something that seems like pure brightness can act like a quiet hand. Now, let the mind drift to something even more ghost-like. Neutrinos. They are among the most elusive travelers in the universe, particles that pass through matter as if it were almost nothing at all. Every second, vast numbers of neutrinos stream through your body without leaving a sensation, without tapping on your skin, without asking permission. Many come from the sun. Others are born in distant stars, in supernova explosions, in nuclear reactions, and deep within Earth itself. They interact so weakly with matter that an entire planet can be, for them, like a thin veil. That's why neutrinos are so difficult to detect. To find them, scientists build enormous detectors, often underground, shielded from other noise, filled with ultra-pure water, ice, or specialized liquids, waiting patiently for the rare moment when a neutrino happens to collide with an atom. And when they do catch one, it's like hearing a single soft footstep in a vast, empty hallway. Studying neutrinos can help reveal how stars work, how the cosmos evolves, and how matter behaves at its deepest levels. They are proof that the universe is full of motion you cannot feel, and full of travelers you will never notice. Now, deeper still, quarks. Quarks are part of what makes protons and neutrons, and therefore much of the ordinary matter around you. But quarks, unlike electrons, do not wander freely. They are never found alone. Nature keeps them bound together by the strong nuclear force carried by particles called gluons, and the strong force behaves in a way that feels almost poetic. The more you try to pull quarks apart, the more the force resists, like a stretchy band that tightens as it's drawn out. If you add enough energy trying to separate them, the universe responds in its own way. New quark-antiquark pairs can form, and instead of isolating a single quark, you end up creating new particles that immediately group themselves again. So quarks remain confined, held in twos, called mesons, or threes, called baryons, like protons and neutrons. They are not solitary travelers. They exist as parts of a whole, and gluons, the glue particles, do something even stranger than that name suggests. Unlike some force-carrying particles, gluons can interact with each other, creating a dense, self-binding web. This is part of why the strong force is so strong, so intensely binding, that it keeps the heart of the atom stable. Without gluons, protons and neutrons would not hold together. Without that, atoms would not form. Without atoms, there would be no chemistry, no bodies, no beds, no soft nights with stories. So as you lie here, letting yourself sink into calm, you can imagine the universe held together by quiet rules and invisible bonds, electron clouds like gentle maps, light that can softly push, neutrinos drifting through like silent wind, and quarks forever cradled by the strongest embrace in nature. Out here in the quiet of night, it can feel as if the world is made of solid, dependable things: your bed beneath you, the air around you, the gentle weight of a blanket. But in the deeper layers of physics, solid turns out to be a kind of slow illusion, held together by fields, relationships, and a few astonishing rules. One of the most important of those rules is connected to something called the Higgs field. The Higgs field is described as an invisible field that fills space, and many particles gain mass through how they interact with it, almost like moving through a subtle, ever-present medium that gives them inertia. and weight. The Higgs boson is a detectable ripple of that field, and it was observed in 2012 at CERN's Large Hadron Collider, confirming a long-standing part of the Standard Model. It's a surprisingly tender thought for a bedtime story that weight is not just a simple built-in trait, but something that arises from interaction, something the universe gives through connection. And without those mass-giving interactions, the familiar structures of atoms and everyday matter would not form in anything like the way they do. Now let the scene widen to what seems like nothing at all. Because even a perfect vacuum, space emptied of air, dust, and light, is not truly empty in quantum physics. Quantum field theory describes empty space as alive with brief, tiny fluctuations. Particle-antiparticle pairs that flicker into existence and vanish again so quickly they can't be directly observed as ordinary particles, even though they're elusive. Their effects can show up in measurable ways, including subtle shifts in atomic energy levels and forces like the Casimir effect between objects in a vacuum. So the quietest space is more like a dark ocean with soft ripples underneath. And the vacuum carries what's often described as zero-point energy that remains even when a system is as low energy as it can possibly be. Some ideas in cosmology explore whether vacuum energy could be related to dark energy, while also noting that theoretical estimates and observations don't neatly match, suggesting something important is still missing from understanding. From there, another pair of concepts enters the story, like twins passing in a hallway. Antimatter. For many kinds of particles, there exists a corresponding antiparticle with the same mass, but opposite charge and related properties. When matter meets antimatter, they can annihilate, converting into energy, often in the form of photons. Antimatter was predicted in 1928 by Paul Dirac, later observed, and it remains rare in the visible universe today. With the imbalance between matter and antimatter still an open question in physics, and this leads, very naturally, to one of the simplest equations that ever carried such a large meaning. Einstein's E is equals to mc squared. It expresses that mass and energy are two forms of the same underlying stuff, meaning that under the right conditions, energy can become particle pairs, and particles can return to energy again. This exchange happens in places of extreme energy, like high-energy collisions, and in the broad story of the cosmos, reminding us that matter is not a permanent substance, so much as a temporary shape energy can take. So while you rest here, safe, still, and sleepy, you can let these ideas drift by like a calming narration. Fields giving weight, emptiness softly boiling with brief possibilities, and matter itself quietly trading places with light. As you rest here, in the soft hush of night, it can be comforting to remember where we are in this relaxing story, settled into a calm rhythm, letting strange ideas arrive gently without needing to be fully solved. Tonight's bedtime story isn't about effort or answers. It's about easing the mind into quiet curiosity and letting that curiosity slowly fade into deep sleep. One of the most peaceful ways to picture the quantum world is this: the universe may not be made of little hard particles drifting through empty space. Instead, It can be described as made of fields, wide, invisible presences that stretch everywhere, even through places that look completely blank. In this view, a particle is not a tiny marble. It's more like a small ripple, a localized vibration, a brief, concentrated wave in the ocean of its field. An electron is an excitation of an electron field. A photon is an excitation of the electromagnetic field. And even when no particles are present, when nothing seems to be happening, those fields are still there, quietly filling space the way night air fills a room. This can feel like a gentle unifying idea. Matter and energy are not separate categories, so much as different expressions of a deeper fabric. This is also why quantum particles can feel so unlike everyday objects. They aren't always best understood as things. They can be understood as events, disturbances in something more fundamental than the objects we're used to imagining. From there, the story becomes even more interconnected, because quantum field theory doesn't just describe matter as fields, it also describes forces this way. Before this framework, it was easy to picture particles as objects and forces as invisible pulls between them. But in the field-based view, what's called a force can arise through fields and the exchange of field excitations, like photons carrying electromagnetic influence between charged particles in a similar spirit. The strong force is associated with fields whose excitations include gluons, and the weak force is associated with fields whose excitations include the W and Z bosons. Gravity may one day fit into a fully quantum description too, but building a complete quantum theory of gravity remains an open challenge. Even so, quantum field theory stands as one of the most successful frameworks in science, with predictions confirmed to extraordinary precision. And now, let the room feel even quieter. Because if space is filled with fields, then even the emptiest space is never perfectly still. The vacuum is not simply nothing. It's more like a background that softly trembles, fields fluctuating in a way that can produce brief, fleeting appearances of virtual particles that vanish almost as soon as they arise. This restless activity is described as being everywhere, between stars, inside atoms, and even in the calm air around you now. And sometimes, that quiet activity leaves fingerprints. One of the most striking examples is the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum, and they can drift inward toward each other due to differences in allowed vacuum fluctuations inside and outside the gap. The effect is small, but it has been measured, and it reminds us that quantum behavior can shape the motion of ordinary objects gently, persistently, without any visible push. This connects to another soft, lingering idea: zero-point energy. Even in a system's lowest energy state, when there's no heat, no light, no obvious motion, quantum theory implies there is still a residual energy that can't be removed completely, linked to the uncertainty principle, because it exists everywhere. Some theories explore whether it could relate to dark energy and the universe's accelerated expansion, though the full story remains unresolved. So if your mind wants an image to hold as it drifts, you can picture the universe as an endless, quiet sea of fields, and everything as a small ripple, and even nothing as a place with a subtle, living hush. As you continue to sink into this nighttime story, it may feel as if the room around you is the only space that matters, calm, still, and safe. But out in the universe, space itself can be active, shaped by energy, curved by gravity, and filled with subtle quantum effects that never fully switch off. Einstein's general relativity offers a quiet, elegant picture. Mass and energy influence how space-time curves, and that curvature guides how matter moves. So, if empty space contains a kind of background energy, what many discussions call vacuum energy, then even regions that look like nothing could still have a role in shaping the universe's geometry and expansion. Exactly how quantum physics and gravity fit together remains one of the hardest open problems in physics, and that uncertainty leaves a wide, mysterious horizon for future understanding, and the vacuum may be more responsive than it seems. Under extremely strong electromagnetic fields, the quantum vacuum can become polarized, virtual charged pairs briefly appearing and shifting in ways that slightly screen or modify the field, as described by vacuum polarization. In even more extreme conditions, theory predicts that strong fields could pull virtual particle-antiparticle pairs apart and make them real, a process often discussed as the Schwinger effect, though direct experimental confirmation is still very challenging because the required field strengths are so immense. So the vacuum is not just a passive background. It can behave like a medium with properties that change depending on the forces surrounding it. HCDR. Now, let your attention drift toward one of the quietest, strangest ideas of all: black holes that aren't perfectly black. Quantum theory predicts that black holes can emit what's called Hawking radiation, an extremely faint glow associated with quantum effects near the event horizon. A common way to picture it is with vacuum fluctuations. Pairs of virtual particles form near the horizon, and if one falls in while the other escapes, the black hole appears to lose energy over time. For large black holes, this radiation is extraordinarily weak, but the idea is profound. Even the darkest objects may slowly change, as if emptiness itself can be coaxed into light, and then the story expands again to the fate of the cosmos. In 1998, observations of distant Type Ia supernovae showed that the expansion of the universe is accelerating rather than slowing down, changing modern cosmology in a single, startling shift. One leading explanation is dark energy, something like an energy built into space itself, pushing the universe outward over vast timescales. If that picture is correct, then the long-term future of the universe may be guided not by stars or galaxies, but by the quiet energy of empty space, stretching everything gently farther apart. And still, the true nature of the quantum vacuum remains deeply uncertain. It sits at the meeting point of quantum theory, relativity, and cosmology areas that each work remarkably well, yet still resist complete unification into a single, final framework. Until that deeper understanding arrives, the space between the stars will remain one of the universe's most mysterious places, apparently empty, and yet never truly nothing. Tonight, as this sleep story continues, everything stays unhurried, like a calm walk through ideas that don't demand anything from you. And now, gently, we arrive at a different kind of machine, a computer not made to feel like metal and noise, but made to follow the soft rules of the quantum world. A classical computer, the kind used every day, works with bits, tiny yes or no units that sit firmly as a 0 or a 1. Each step is definite. Each operation is clear. It's like walking along a path of stones, one after another. But a quantum computer uses qubits, and a qubit can be held in a superposition, described as a blend of 0 and 1 at the same time, with different weights, like a quiet mixture of possibilities. Because of that, quantum computing can feel like it's exploring many routes at once, not by magic, not by guessing, but by letting probability and interference do what they naturally do in a soothing way. You can picture it like this. Instead of opening one door, checking one room, and moving on, it's as if the system sets up many doors at once, many quiet maybes, then arranges them so the paths that lead nowhere gently cancel out, and the path that matters becomes clearer. This is where the promise comes from. As more qubits are added, the number of combinations that can be represented grows incredibly quickly. With just a small number of qubits, a quantum system can describe a vast landscape of possibilities in one moment. Still, this delicate power comes with a softness that's hard to protect. Quantum states are fragile. Tiny disturbances from heat, vibration, stray electromagnetic noise can disrupt them. Errors appear easily, and keeping a quantum system stable long enough to perform useful work is one of the biggest engineering and scientific challenges in the field. So quantum computers are still young. They're learning, in a sense, how to hold onto their quiet, shimmering states without being pulled back into ordinary certainty too soon. And that brings us back to measurement. Because a qubit doesn't keep its blended possibilities forever. When it's measured, it gives a single outcome, like the gentle closing of a book to one page. That means quantum algorithms have to be designed with care. They need to shape the evolving probabilities so that, by the time the measurement happens, the chance of reading the best answer is high, while less useful answers fade into the background. And here, entanglement returns like an old theme in a calm piece of music. Entanglement is not only a curiosity for quantum theory. In quantum computing, it becomes a resource. When qubits are entangled, they share a combined description, allowing patterns of correlation that classical bits simply cannot reproduce. It can link different parts of a calculation together, tying pieces into a single, coordinated behavior, like dancers moving as one, even when separated across the stage. Entanglement can also support approaches to error correction, ways of detecting problems without directly staring at a fragile quantum state and collapsing it too soon. Without entanglement, much of quantum computing's potential advantage would soften away. Then there are the algorithms, the special instructions that make use of these rules. Some quantum algorithms are famous because, in principle, they can outperform classical methods for specific tasks. One well-known example is Shor's algorithm, often discussed for its ability to factor large, numbers far more efficiently than known classical approaches. Something that matters because many common encryption systems rely on factoring being hard. Another is Grover's algorithm, which offers a speed up for searching through unsorted possibilities, like finding one marked grain of sand on a wide beach, but doing it with fewer steps than classical searching would require. Quantum computers are not faster at everything, but for the right problems, the advantage could be enormous. And that's why so many researchers, companies, and governments are paying close attention, because certain kinds of chemistry, optimization, and cryptography might become possible in ways that feel almost like waking up with a new sense, which leads to a final gentle idea for tonight: quantum cryptography. Classical cryptography often rests on mathematical difficulty, problems that are simply too slow to solve with ordinary computers. But quantum cryptography aims for something different: security rooted in physics itself. In methods like quantum key distribution, encryption keys are shared using quantum states of light. If someone tries to secretly observe the key in transit, the act of measuring disturbs the states, leaving traces that can reveal an intrusion. It's a quiet form of protection, not secrecy by hiding, but secrecy by the universe, refusing to let information be copied perfectly without consequence. And now, as your breathing slows again, you can let all of this settle into a calm feeling rather than a technical lesson. That computation, like everything else in this bedtime story, can become softer and stranger at the smallest scales, and that the quantum world offers not just mysteries, but new ways of shaping possibility. As this bedtime story continues, everything stays soft and steady, as if each idea arrives on quiet feet, careful not to wake the mind. And tonight, the quantum world isn't only about mysteries in textbooks, it's also about tools, gentle instruments that can listen to reality in a way that ordinary devices simply can't. Quantum sensors are a beautiful example. By using quantum effects like superposition and entanglement, these sensors can detect the tiniest changes, small shifts in magnetic fields, faint variations in acceleration, or delicate differences in time itself. They can be so sensitive that they notice whispers classical instruments would miss, subtle changes that might come from hidden structures underground, tiny gravitational variations, or minute signals inside living bodies. Some approaches use clouds of ultra-cold atoms, suspended and measured with exquisite care. Others use special defects in diamonds, places where the structure is slightly different, creating a sensitive quantum listener inside the crystal. The overall feeling is the same. Instead of forcing nature to speak loudly, quantum sensors learn how to hear the quietest parts of the universe. And the calmer your mind becomes, the more fitting that seems, because sleep, too, is a kind of listening. Not for danger or urgency, but for soft signals that tell the body it's safe. Now, drifting beside sensing, there is another quantum phenomenon that feels almost like a lullaby about smoothness, superconductivity. In ordinary wires, electricity meets resistance. A little energy is always lost as heat, the way footsteps always make some sound on a wooden floor. But in certain materials, often when they are cooled to extremely low temperatures, resistance can drop all the way to zero. In that state, an electric current can flow without energy loss, sustained in a way that feels almost endless. This happens because, at low enough temperatures, electrons can pair up and move in a coordinated, quantum coherent way, less like separate individuals, and more like a single shared wave gliding through the material. Superconductors already exist in the world around you, quietly doing practical work. They help power MRI machines, guide particle beams in accelerators, and make magnetic levitation possible in some train systems. And there's an ongoing dream in physics and engineering. If superconductivity could be achieved at everyday temperatures, it could transform energy transmission and many other technologies. From there, the story reaches outward again, toward connection across distance. Just as ordinary computers are linked by the internet, future quantum computers may be linked by quantum networks. These networks aim to use entanglement and techniques like quantum teleportation of states to share information in ways that are fundamentally difficult to intercept without leaving traces. The challenge is delicate. Entanglement is easily disturbed, and maintaining it over long distances requires careful engineering, using fibers, satellites, and devices designed to extend quantum links step by step. If such a network becomes reliable at large scale, it could enable ultra-secure communication, distributed quantum computing, and even new kinds of sensing that work across wide regions, like turning the planet into a softly connected web of quantum relationships. And now, to keep time in this gentle story, we come to one of the most quietly astonishing human inventions: atomic clocks. The most accurate clocks don't use gears or pendulums. They use the natural vibrations of atoms as their ticks. Some of the most advanced systems cool atoms to extremely low temperatures and hold them steady with lasers, so their oscillations can be measured with breathtaking precision. These clocks are so steady that their drift is incredibly small over immense spans of time. And that precision is not just a scientific curiosity. It supports technologies that depend on timing, like navigation and telecommunications. As atomic clocks become even more sensitive, they may be able to detect tiny differences in how time passes from place to place, subtle effects linked to gravity and height, as predicted by relativity. So, while quantum computers often sound like the headline of the future, much of the quantum revolution is already here in quieter forms. Sensors, clocks, superconductors, communication experiments, and simulators that help researchers model complex materials and molecules. And for tonight, you can let that be the feeling that remains, that the quantum world isn't only far away. It's already woven into tools that measure, heal, guide, and connect, all while you lie here, letting your breathing slow and letting the day dissolve into rest. As the night deepens, the story turns gentle again toward meaning, toward the ways people have tried to explain what quantum mathematics is really saying, without disturbing its quiet mystery. The equations work beautifully, but their interpretation can feel like listening to a language that describes reality, while also refusing to say, plainly, what reality is. One of the most taught approaches is often called the Copenhagen interpretation, associated with ideas from the late 1920s linked to Niels Bohr and Werner Heisenberg. In its practical spirit, a quantum system is described by a wave function that gives probabilities, and a definite outcome is connected to measurement, often spoken of as collapse. Even though the exact status of collapse in Copenhagen-style views is debated, it's useful and experimentally successful, yet it can feel philosophically unsettling. Were the properties real before measurement? Or is the wave function mainly a tool describing what can be predicted? If Copenhagen feels like accepting uncertainty as part of the universe, another view tries to keep the equations and avoid collapse entirely. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that the wave function never collapses. Instead, all outcomes occur, each in its own branching world. In that picture, when a quantum event has multiple possible results, reality doesn't choose just one, it branches, like a tree quietly growing new limbs in the dark. This approach is elegant in one way, but it raises its own heavy questions about what it means to experience a single outcome, and what choice means inside a constantly branching multiverse. Then there is another path, one that appeals to minds that prefer a more deterministic feeling story. Pilot wave theory, also called Bohmian mechanics, keeps the Schrödinger equation, but adds additional structure. Particles are taken to have definite positions, guided by a wave-like pilot field that shapes their trajectories. This can reproduce the usual predictions of quantum mechanics while changing the underlying picture of what's happening, though it typically involves accepting a kind of non-locality in the guiding dynamics. For some, it feels like returning to a calmer, more clockwork universe, though the clockwork is hidden behind a wave. Other approaches suggest something different again. Maybe superpositions don't last forever, even without observation. So-called collapse theories propose that quantum states have a small, built-in tendency to reduce spontaneously, with the effect becoming overwhelmingly fast for large systems, offering one possible reason why everyday objects don't appear in obvious superpositions. These models aim to explain the quantum to classical transition without requiring consciousness or branching universes, and they motivate experiments searching for tiny deviations from standard quantum predictions. They are not the mainstream default, but they remain part of the ongoing attempt to understand measurement more deeply. And then, quietly, there is decoherence, less an interpretation and more a physical process. Decoherence describes how interaction with the environment, air molecules, stray light, vibrations, can entangle a quantum system with its surroundings, so that interference between different superposed components becomes effectively unobservable. It helps explain why quantum strangeness fades so quickly for macroscopic objects, making them appear classical in practice. But even with decoherence, a subtle question remains. It can explain why superpositions become hidden, yet it doesn't by itself fully answer why one definite outcome is experienced. And for tonight, you don't need to pick a side. You can let these interpretations be like different bedtime story lanterns, each casting a slightly different glow on the same quiet landscape. While your own mind does what it does best at this hour, softens, slows, and drifts gently toward sleep. As this relaxing nighttime story continues, the questions become quieter, but also deeper, as if the mind is floating above a dark ocean and sensing a vast depth below. At the heart of quantum mechanics, there's still a puzzle that refuses to fully settle: the measurement problem. Quantum equations describe a smooth, continuous evolution, like a calm tide changing shape over time. And yet, when a measurement is made, we experience a single outcome, as if the many gentle possibilities suddenly narrow into one clear result, often described as wave function collapse. Whether that collapse is a real physical process or a change in how information is represented remains debated, and different interpretations answer in different ways without one final, proven resolution. This is why the measurement problem is more than a technical detail. It touches the nature of reality itself, whether the world has definite properties when no one is looking, or whether definiteness is something that appears only through interaction and observation. And once that door is open, another question sometimes drifts in, soft, controversial, and often misunderstood. Could consciousness itself matter? There has been a historical interpretation, sometimes called the von Neumann-Wigner view, associated with discussions by John von Neumann and Eugene Wigner, in which consciousness is postulated to play a special role in collapse. Most physicists today do not treat this as the leading explanation, and popular culture often exaggerates observer effects in ways that go beyond what experiments actually show. Still, the idea lingers in the background of the story, not as a settled truth, but as a reminder of how strange it feels that physics can describe possibilities so well, while leaving the appearance of a single experienced outcome so open to interpretation. Now, let the story shift gently from what is real to how to describe what is real. Because quantum mechanics doesn't only challenge intuition, it also challenges the ordinary structure of logic. In classical thinking, statements tend to be neatly true or false, like a lamp that is either on or off. But quantum theory uses a mathematical framework, Hilbert space, where the outcomes you can speak about depend on how you ask, and the order of measurements can matter because some observables do not commute. That means measuring one quantity can disturb what would be found in another, and swapping the order of measurements can change what happens, something that has no everyday analog in classical physics. And this brings the story to one of the most emotionally charged ideas in all of science: randomness. In quantum mechanics, certain events, like the outcome of a measurement, are treated as fundamentally probabilistic, not merely unknown due to limited instruments. For some minds, that feels unsettling, like the universe is not a clockwork machine, but something closer to chance. For others, it feels almost gentle permission for novelty, for openness, for a reality that doesn't always demand a single predetermined line. Finally, at the edge of this part of the story, quantum physics leans towards space and time themselves. Physicists still seek a complete framework that unifies quantum theory with gravity. And the difficulty of that task suggests that space and time may not be the final stage on which reality plays out, but part of the deeper structure being described. Ideas in quantum gravity sometimes explore whether space-time could have discrete structure or emergent behavior, though no single theory is confirmed. So, the bedtime feeling to carry forward is simple at the deepest level. Even the concepts of where and when may be softer than they seem. As this gentle bedtime story continues, the world feels very still, and it's easier to imagine the smallest rules of nature becoming visible, like faint patterns appearing on dark water, because sometimes quantum behavior doesn't stay hidden inside atoms. Sometimes it spills upward into things that can be seen, measured, and almost, in a way, felt. One of the most enchanting examples is superfluid helium. When helium is cooled to just a little above absolute zero, below about 2 Kelvin, it can change into a state called a superfluid. In this state, it loses viscosity, the internal thickness that normally slows liquids down, and without that internal friction, the liquid behaves in ways that seem to ignore common sense. Superfluid helium can creep up the walls of its container in a thin film, as if the surface itself is a gentle path. It can slip through tiny pores that ordinary liquids can't pass. And in a closed loop, it can keep circulating without slowing, as though it has forgotten how to waste energy. This isn't because it becomes magical. It's because the helium atoms begin to share one coordinated quantum state, moving together like a single, perfectly synchronized wave. A whole liquid, acting like one quiet decision. Not a crowd of individuals, a single flowing we. Nearby in this family of strange, calm matter is something even more dreamlike, the Bose-Einstein condensate. This state of matter was predicted in the 1920s by Satyendranath Bose and Albert Einstein. It forms when certain atoms are cooled to an extremely tiny fraction of a degree above absolute zero. At those temperatures, the wave-like nature of atoms becomes impossible to ignore. Their individual wave functions begin to overlap, and what used to be many separate atoms becomes one shared quantum state spread across the entire sample. In a sense, the condensate behaves like a single superatom, with countless particles moving in unison. Bose-Einstein condensates give scientists a way to study quantum effects on a scale large enough to observe directly interference patterns, superfluid-like flow, and other behaviors that usually belong to the microscopic world. It's a quiet reminder that matter has more than 3 familiar faces. Not only solid, liquid, and gas, but stranger, softer forms that appear when the universe is cooled into silence. Now, let the story drift to electrons, tiny, restless characters that can also organize themselves into new kinds of order. In special conditions, when electrons are confined to an ultra-thin layer, cooled close to absolute zero, and placed in a strong magnetic field, they can enter a regime known as the quantum Hall effect. Here, electrical resistance doesn't change smoothly. It locks into precise, quantized values, stable integers or fractions, remarkably robust. Even when the material has impurities, it's as if the electrons stop behaving like separate particles and begin behaving like a collective pattern, a shared arrangement that has its own rules. In some versions, the excitations are described as quasi-particles that carry fractional electric charge, an idea that feels like a whisper from a deeper layer of reality, where particle is not always a simple category. This effect has reshaped condensed matter physics and helped reveal how deeply mathematics, especially the idea of topology, can appear in the behavior of real materials. And that brings us naturally to topological materials. These are substances whose electronic behavior is guided not only by what they are made of, but by the shape of their quantum states in an abstract mathematical sense. One of their most calming features, calming at least to engineers and physicists, is that they can host special surface or edge states that are unusually resistant to disturbance, even if the material has defects. Even if it isn't perfectly clean, these states can remain protected by the material's topology, as if the universe has built a safeguard into the geometry of the system. Because of that robustness, topological ideas have become promising for building more stable quantum technologies, including potential qubits that resist noise better than today's delicate designs. And now, one last quiet marvel to close this part: quantum tunneling. In classical physics, a barrier is a barrier. If you don't have enough energy to climb over it, you simply can't pass through. But in quantum mechanics, particles are described by wave functions, spread out possibilities. And sometimes, those wave functions extend into and beyond a barrier, leaving a small probability of the particle appearing on the other side, not by going over, but by passing through in the most literal, impossible-sounding way. Tunneling is not a rare trick. It plays a role in nuclear processes inside stars, and it shows up in human technology too, especially as electronic components become extremely small, where tunneling can create unwanted leakage currents through barriers that are too thin to fully contain electrons. So even solidity has softness in it. Even walls have a small chance of being crossed. And for a sleepy mind, that can be a comforting thought. Because if nature itself is allowed to be fluid, uncertain, and quietly surprising, then you can be too. You can loosen your grip on the day. You can let your thoughts thin out, and you can drift gently into rest. As the night carries on, the story drifts outward, beyond rooms and cities, beyond even the earth, into the slow-burning quiet of space. And it turns out that starlight, something that feels so steady, so dependable, depends on a quantum permission. In the heart of a star like the sun, hydrogen nuclei are positively charged, and they strongly repel each other. In a purely classical picture, you'd expect them to need far more energy to push close enough to fuse, but quantum tunneling offers a different path. Instead of always needing to climb over the hill of electric repulsion, nuclei have a small chance to slip through it, appearing close enough for the strong nuclear force to take hold and bind them together. When that happens, energy is released. And that steady release is what powers the sun's warmth and light, and the long, patient brightness of stars across the universe. It's a comforting thought, really, that the cosmos is not lit only by force, but also by probability. From stars, we return to Earth back into human hands. human laboratories, and the quiet craft of turning quantum behavior into working tools. One of the simplest, strangest devices is the Josephson junction. Imagine two superconductors separated by an extremely thin barrier. In a normal world, that barrier would stop current, but in the quantum world, paired electrons in a superconductor, Cooper pairs, can tunnel across. A current can flow without the usual resistance, in a way that feels like a whisper passing through a closed door. And when a voltage is applied, this tunneling behavior can produce oscillations with remarkably precise frequency relationships. That precision is why Josephson junctions are so valuable in ultra-sensitive measurement devices and in certain standards for electrical measurement. They also appear in many superconducting quantum computer designs, where they help form the delicate circuits that behave like qubits, quiet, responsive, and easily disturbed. Now, here is another idea that sounds almost like a paradox, yet remains gentle when you let it be. Sometimes, observing a system repeatedly can keep it from changing. This is known as the quantum Zeno effect. If measurements happen frequently enough, the system can be reset into its current state again and again, slowing its evolution, almost freezing it in place. It turns the usual intuition inside out. Observation doesn't only reveal, it can also restrain. It can shape the story by refusing to let the next page turn. And while that might feel eerie in daylight, at night it can be soothing. A reminder that slowing down is not failure. Sometimes, slowing down is simply what happens when attention becomes steady. From there, the story returns to floating, because superconductors can also lead to a kind of levitation that looks like calm magic. When certain materials become superconducting, they can expel magnetic fields from their interior, and in some conditions, they can also pin magnetic field lines into place. The result can be stable levitation, a superconductor hovering above a magnet, locked into a position, resisting slips and slides. It's not just floating. It's floating with stillness, held in a quiet balance, a demonstration that contact isn't always necessary for support, and that the universe has more than one way to hold something up. And then, one of the most tender possibilities of all, that living things may sometimes make use of quantum effects. Some research suggests that certain biological systems might preserve hints of quantum coherence long enough to be useful, like excitations in photosynthesis, appearing to explore multiple pathways to find efficient energy transfer. There are also ideas, still being investigated, that some animals may sense magnetic fields using quantum-sensitive processes, and even proposals that smell could involve tunneling-like behavior at the molecular scale. Nothing here needs to be taken as final or proven in every detail, but the direction is gentle and beautiful. Nature may have been quietly using quantum rules long before humans had names for them. Finally, we drift back to the beginning of everything. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense, fields and energy in restless motion. Tiny fluctuations, rooted in quantum uncertainty, would have been present even then. Small variations that, as the universe expanded, were stretched outward. Over vast time, those slight irregularities became seeds, the beginnings of structure, the faint first suggestion of where galaxies would gather, where stars would ignite, where planets would form. So, in a sense, the universe's grand architecture may trace back to quantum softness at the start, the smallest tremble becoming the widest pattern. And now, as you rest with this gentle bedtime story, you can let that idea settle like a warm blanket, that the cosmos is shaped by quiet chances, that the brightest stars depend on tiny probabilities, and that even your own thoughts can become like quantum ripples, appearing, fading, and finally smoothing into silence. As this sleep story moves forward, it feels as if we're floating farther from the everyday world, watching the universe from a peaceful distance, where even the largest things begin with the smallest hints, those early quantum ripples, tiny variations, so small they sound almost imaginary, became the seeds of everything structured you see in the night sky. As the universe expanded and cooled, gravity could begin to amplify those slight differences, denser regions gently attracting more matter, growing over long stretches of time into vast clouds, then stars, then galaxies. The great cosmic web of clusters and filaments can be traced back, in modern cosmology, to these early seeds, quantum fluctuations stretched to cosmic size Big Think. And this connects naturally to another early universe idea, inflation. Cosmic inflation proposes that the universe went through a brief period of extremely rapid expansion in its earliest moments. In inflationary models, quantum fluctuations in the inflation field are stretched outward, becoming the primordial perturbations that later grow into the large-scale structure of the universe. So, in a quiet way, quantum uncertainty may have helped sketch the universe's first blueprint, an invisible pattern that gravity later traced into galaxies and stars Big Think now. Let the story drift towards something darker, but not frightening, black holes. They are often introduced through general relativity, gravity, so intense that an event horizon forms, a boundary beyond which light cannot escape. And yet, black holes also sit at the edge of quantum theory, because quantum fields behave in surprising ways near horizons. That's where Hawking radiation enters the story. Quantum field effects in curved spacetime predict that black holes can emit a faint thermal radiation, slowly losing mass over time. Understanding black holes completely is one reason physicists keep searching for a unified description of quantum mechanics and gravity. They may be one of the best places to learn how the smallest rules of particles connect with the largest structures of spacetime. And far from black holes, in the wide emptiness between galaxies, another mystery continues: dark energy. Observations in 1998 showed that the expansion of the universe is accelerating, and dark energy is the name given to whatever drives that acceleration. One idea explored in cosmology is that dark energy could be related to vacuum energy, the background energy associated with quantum fields, even in empty space, though theoretical predictions and observed values don't match neatly, making it a major puzzle. And when the mind reaches for the deepest layer of all, it sometimes arrives at the possibility that space itself may not be perfectly smooth. Some approaches to quantum gravity suggest a fundamental length scale, often associated with the Planck length, where space-time might have a discrete or pixel-like structure, rather than being infinitely divisible. Directly detecting such granularity is beyond current technology, but researchers look for subtle hints in how high-energy particles or quantum fields behave over vast distances. For now, it remains an open possibility, one more quiet sign that the universe may be built from deeper building blocks than everyday intuition suggests. And finally, there's a soft, speculative thought that ties many of these themes together. If quantum entanglement is truly universal, then perhaps the cosmos is not a collection of separate pieces, but a single connected quantum system, vast, woven, and coherent in ways still only partly understood. This idea isn't settled science, but it fits naturally with how modern physics keeps revealing that separation is sometimes only a surface appearance. So as you rest, safe in your room, breathing slowly, you can let this part of the nighttime story fade into a calm feeling that galaxies may be the grown-up shadows of tiny early ripples, that even black holes may glow softly at the edges, and that space itself may be quieter, deeper, and more mysterious than it seems. As the night grows deeper, this calming narration moves toward one of the biggest open questions in all of science: how the universe holds its rules together. Quantum mechanics describes the tiny world with extraordinary success, and general relativity describes gravity and space-time with equal elegance. Yet bringing them into one consistent picture remains unfinished. That unfinished goal is often called quantum gravity. It's the search for a framework that works for subatomic particles and for massive objects, for the beginning of the universe and the edges of black holes. One set of principles that doesn't change its mind depending on scale. There are multiple approaches explored in research, and no single one has been confirmed as the final answer. And in the middle of that search, there is a thought so strange, it almost feels like poetry. Wormholes. Wormholes are hypothetical connections in space-time, tunnels that would link distant regions through a shortcut. In modern theoretical discussions, one proposal known as ER equals EPR suggests a relationship between entanglement, EPR pairs, and wormholes, Einstein-Rosen bridges, loosely hinting that entanglement might have a geometric shadow in spacetime. It's still speculative, but it offers a bridge between the language of quantum links and the language of curved geometry, as if connection and space might be two ways of describing the same deeper structure. And this is why quantum physics can feel less like one chapter of science and more like the frame around the whole book. Quantum theory already underlies the behavior of atoms and molecules, the foundations of chemistry, and the structure of matter. Yet it also leaves mysteries open: measurement, interpretation, and the relationship with gravity, suggesting that something deeper may still be waiting beneath what's already known. Some physicists suspect that understanding quantum mechanics more fully could reshape the way reality itself is described, not just the way particles behave. And when the mind returns to the most familiar example, simple and famous, it finds the double-slit experiment again, quietly demonstrating how looking is never entirely passive. When which path information is obtained, the interference pattern disappears, showing that the act of measurement changes what is observed. In quantum mechanics, to observe is to interact, and interaction becomes part of the outcome. So for tonight, you can let the idea land softly that the universe may have one set of rules on the surface and a stranger, gentler set underneath. That gravity and quantum physics are still learning how to speak the same language, and that, even in a bedtime story, it's okay not to know the final answer, because your only job now is to rest. As the night continues, we return to a gentle theme you've heard before in this bedtime story: how the quantum world asks us to soften our need for perfect certainty and to rest inside, maybe. One of the clearest examples is the uncertainty principle, associated with Werner Heisenberg. It says there are pairs of properties, like position and momentum, that cannot both be pinned down with unlimited precision at the same time. The more tightly one is defined, the more the other slips into blur, not because tools are clumsy, but because the quantum world itself doesn't offer both as perfectly sharp facts at once. So at tiny scales, reality can feel less like a crisp photograph and more like a soft watercolor edges present, but never absolute until interaction makes a choice. And that leads naturally to the wave function, the mathematical description that holds the possible outcomes of measurements and the likelihood of each. It doesn't promise a single future, it describes a spread of futures, each weighted like a quiet probability. Before measurement, the system is represented in a way that includes multiple possibilities, what we often call superposition. And when a measurement happens, we observe one outcome, often described as collapse, while the deeper question of what collapse is, physically, remains part of the measurement problem. Different interpretations speak differently here, and none has closed the conversation completely. Superposition itself is one of the dreamlike heartbeats of quantum theory. A particle can be described as occupying multiple states at once, multiple paths, multiple locations, multiple options, until the environment or a measurement forces a definite result. This delicacy is why superpositions are hard to keep in the noisy, warm, everyday world, and why quantum engineers work so carefully to protect qubits in quantum computers. And then, like a soft refrain, the story returns to entanglement. Entanglement allows two or more particles to share a single quantum description so completely that measuring one strongly constrains what will be found when measuring the other. Even across large distances, these correlations do not allow faster-than-light messaging, but they still challenge the everyday feeling that distant objects are fully independent once separated. It's one of the most tested and conceptually demanding features of quantum mechanics, an invisible link that behaves like shared identity stretched across space. So tonight, you can let all of this settle into a calming thought. You don't have to know everything at once. You don't have to define every edge perfectly. Like the quantum world itself, you can rest inside gentle uncertainty and allow sleep to choose the next moment for you. As the night holds steady, we return to that quiet, persistent theme in this bedtime story: connection that runs deeper than distance, and questions that stay gentle, even when they feel enormous. For a long time, some scientists hoped entanglement had a hidden, classical explanation. The dream was simple. Perhaps particles carry secret instructions, hidden variables that decide outcomes in advance. Then the universe could remain tidy and local, with no strange, long-distance coordination. But the more carefully physicists tested entanglement, the harder that tidy picture became to keep. John Bell's work showed a way to check whether local hidden variables could explain the correlations entanglement produces. And across many experiments inspired by Bell's theorem, the observed correlations have matched quantum mechanics rather than any purely local hidden variable account. So the universe seems to require something unfamiliar. Either the world is not local in the comforting, everyday sense, or the idea that particles hold definite properties before measurement must be handled far more carefully than classical intuition expects. It's a strange lesson, and yet, for sleep, it can also be soothing. Reality is not obliged to be simple in the way we first imagine. The mind can stop wrestling and simply let mystery exist. From here, the story drifts into an even more provocative possibility. Some modern ideas suggest that entanglement might not just live inside space-time. It might help shape space-time in certain approaches to quantum gravity and holography. Researchers explore whether geometric relationships, distance, connectivity, the shape of space could emerge from patterns of quantum information, especially entanglement. It's as if the universe might be built from relationships first, and the stage we call space might be something that arises afterward. This remains speculative, but it offers a hauntingly elegant picture that the fabric of reality could be woven from invisible links, not from solid objects alone. And if that idea is even partly true, it invites an image that feels almost like poetry. That the cosmos is a vast web, not just a web of galaxies, but a web of correlations, countless quiet connections threading through the underlying fields of nature. In that picture, separateness becomes a surface appearance, like islands that look distinct until you notice they share the same ocean beneath. At the same time, entanglement can be delicate. In many real environments, interaction with surrounding air, light, heat, and vibration causes decoherence, the slow leaking away of quantum information into the environment, making entanglement hard to maintain. That fragility is one of the practical challenges for quantum computing and quantum communication, where entangled states are precious. And yet, under the right conditions, entanglement can also be surprisingly resilient. Certain materials and carefully designed protocols can help preserve it longer, strengthen it, or restore useful correlations, turning something fragile into something workable. Now, with the same slow calm, we return to the vacuum. Even when space appears empty, quantum fields are never perfectly still. Fluctuations can be described as brief, fleeting pairs, virtual particle and antiparticle-like disturbances, appearing and vanishing, leaving subtle fingerprints in measurable effects. Those fingerprints show up in tiny shifts in atomic behavior, in delicate forces between objects, and in the way quantum fields behave near extreme gravity. Which brings us back, softly, to black holes. Hawking radiation is one of the most famous signs that black holes are not purely classical objects. Quantum field effects near the event horizon imply a slow, faint emission of radiation, meaning black holes can lose energy over very long times. It's an idea that sits right at the border between quantum mechanics and gravity. And with it comes one of the deepest open questions still discussed. What happens to information that falls into a black hole? Even tonight, you don't need to solve it. You only need the feeling of it. That emptiness is active, that connection can be stronger than distance, and that the universe is still, in many places, unfinished in our understanding. And that's okay, because you are allowed to be unfinished tonight too. You can let your thoughts soften and let sleep arrive without needing a final answer. As this nighttime story continues, everything grows quieter again, as if the universe itself is lowering its voice, inviting you to relax into the spaces between thoughts. And tonight, we return to one of the strangest spaces of all, the vacuum. At first glance, empty space seems like a blank stage, nothing there, nothing happening. But in quantum physics, the vacuum is not a simple nothing. It's the lowest resting state of fields that still exist everywhere. And those fields can never be perfectly still. Even empty space carries a faint, persistent background activity, subtle fluctuations that can leave real effects. And if the vacuum holds energy, even a tiny amount, then it matters cosmically. Because in gravity, energy doesn't just sit quietly. Energy influences the curvature and behavior of space-time. So a small, steady vacuum energy could act like a gentle pressure built into space itself, one that can push outward, stretching the universe wider over time. This is one reason vacuum energy is often discussed alongside dark energy, the mysterious component associated with the universe's accelerated expansion. And yet, there is a deep, unsolved tension here. When physicists estimate vacuum energy using quantum ideas, the simplest calculations don't seem to match what astronomers observe. The gap between theory and observation is so large that it's often treated as one of the most troubling open problems in fundamental physics. So the vacuum remains a mystery with a quiet, heavy weight. Is its energy truly constant? Could it change slowly, like a dimmer switch turning over cosmic time? Is the vacuum we live in the deepest possible resting state, or only a local valley, calm for now, but not the final floor? In the soft language of this bedtime story, the vacuum feels less like emptiness and more like a hidden ocean, still on the surface, but full of depth. From there, the story drifts to something that sounds abstract, but shapes many of the most practical quantum ideas, logic itself. In ordinary life, logic feels crisp. A statement is true or false. A door is open or closed. But quantum systems don't always behave as if properties are simply waiting with fixed answers. Some outcomes depend on context, and the order of certain operations can matter. So the neat, rigid structure of everyday reasoning becomes less reliable. This is part of what makes quantum computing possible. A qubit can hold a blend of possibilities, and a quantum algorithm can choreograph how those possibilities interfere, allowing some to fade and others to stand out, until a final measurement reveals one definite result. Even logic in the quantum world can feel like a soft landscape rather than a hard line. And at the heart of that softness is probability. In classical physics, randomness often feels like ignorance. If you knew enough, you could predict everything. But quantum mechanics changes the mood. Even with the best possible description of a system, it often offers only probabilities, likelihoods, not guarantees. Radioactive decay, for example, doesn't come with a countdown clock you can read in advance. Many measurement outcomes are not predictable as certainties, only as chances. That shift from determinism to probability remains one of the deepest philosophical turns in science. And finally, where probability meets gravity, the story becomes wild again. Even when told gently, black holes already stretch imagination. But theoretical physics explores even stranger possibilities at their edges. Wormholes as hypothetical shortcuts, white holes as time-reversed cousins, and ideas like firewalls, controversial proposals that arise when trying to reconcile quantum theory with what gravity seems to demand. These ideas are not settled facts. They are signposts in the fog, showing where understanding is incomplete. And perhaps that is the calmest truth of all to bring into sleep. Quantum physics reaches everywhere from tiny particles to the largest structures of the cosmos. It helps explain matter, light, chemistry, stars, and the growth of galaxies. And still, it leaves wide room for unanswered questions. Tonight, you don't have to carry those questions like a burden. You can let them be like distant stars, present, beautiful, unresolved, and far enough away that you can simply rest. And now, very gently, we begin to drift back from the smallest places in the universe. Back from the quiet mathematics, the invisible fields, and the delicate probabilities, and back into the simple calm of this moment, where your breathing can slow, and your thoughts can loosen their grip. Tonight, in this relaxing story, this soft bedtime story made to help you fall asleep, we wandered through a realm where reality doesn't always behave the way the waking mind expects. We moved through a world where particles can act like waves, where possibilities can overlap, and where a simple act of measuring can change what becomes definite. We lingered with the strange beauty of superposition, with the gentle mystery of entanglement, with the idea that connection can run deeper than distance. We let our imagination brush against quantum fields and the quiet hum of empty space, learning that even a vacuum is not a blank nothingness, but a subtle background that never fully goes still. We also saw that matter can take on forms that feel almost dreamlike, liquids that flow without friction, states where countless atoms move as one, and tiny, tunneling chances that help stars shine through the long patience of cosmic night. And maybe, as you rest, some of these ideas are already beginning to soften at the edges. That's perfectly okay. You don't need to hold onto every fact. You don't need to remember every term. This is a gentle bedtime, not an exam. The purpose of this nighttime story is not to make you think harder, but to help you think less, more slowly, until thinking becomes something like distant weather present, but no longer important. If a few images stay with you, let them stay lightly. A faint ripple in a field, a quiet coin of energy, a thread of connection stretching across darkness. A universe that is not only made of things, but made of relationships. And if the questions return, big questions, old questions, let them return without urgency. Quantum mysteries do not ask to be solved tonight. They can simply exist, like stars you don't need to count. Unhurried, unbothered, patient. If you found calm here, or if this soothing story gave you even a small moment of wonder, you can always come back to Sleepy Story Facts whenever you need a quiet place to rest. And if another day you feel like supporting this space in a gentle way, you'll know what to do. No pressure, no rush. For now, let the universe continue without your attention. Let the smallest particles keep whispering their rules. Let the vast galaxies keep turning in silence. And let your own mind drift down, deeper, softer, until even the thoughts become quiet.